3 weeks ago, 4 astronauts aboard NASA's Artemis II spacecraft broke a record that had stood for over half a century. They traveled more than 252,000 miles from Earth, farther than any human being has ever gone. And yet that distance, the farthest our species has ever reached, is less than 1% of the way to Mars, even at its closest approach. It is not even a rounding error on the scale of our own solar system. So here is the question nobody wants to answer honestly. How far could humans actually ever travel in space? Not in science fiction, not in dreams. In reality, the answer is closer and more final than you think. If you find yourself thinking about this kind of question, the kind that stays in your head for days, consider hitting that like button and subscribing. It helps more than you might expect, and it means we get to keep making these deep dives together. Now, get yourself comfortable. Let's begin. On April 6, 2026, 4 astronauts aboard NASA's Orion spacecraft passed a mark that no human being had crossed in more than half a century. Commander Reed Wiseman, pilot Victor Glover, and mission specialists Christina Koch and Jeremy Hansen surpassed the distance record set by the crew of Apollo 13 in 1970. They traveled more than 252,000 miles from Earth, farther from home than any person in history. The moment was electric. Wiseman's voice crackled through the communication link as Orion swept past the moon, and he spoke not only to mission control but to every generation that would follow. He challenged the next wave of explorers to make sure the record would not stand for long. The whole world watched. Social media erupted. Headlines declared a new chapter in human exploration. And in every meaningful sense, the celebration was deserved. Artemis II represented the first time human beings had left low Earth orbit since December of 1972. For 53 years, our species had stayed close, circling our planet in stations and shuttles, never venturing beyond the thin envelope of near-Earth space. Artemis changed that. Humans were back in deep space, but here is what the celebration obscured. 248,000 miles sounds enormous. It is enormous by any standard a human body can feel. If you drove that distance in a car at highway speeds, the trip would take roughly 5 months of continuous driving without sleep, without stopping, without ever pulling over. That number exceeds the total distance most people will ever travel in their entire lives, multiplied by 100. It is a genuine achievement of engineering, physics, and human courage. And it is nothing. Mars, the very next destination on the list, orbits the Sun at an average distance of roughly 140 million miles from Earth. That number fluctuates dramatically depending on where both planets sit in their orbits. At its closest approach, Mars can come within about 34 million miles. At its farthest, the gap stretches to 250 million miles. A realistic crew mission would likely launch during a favorable window and travel somewhere between 30 and 60 million miles to reach the planet. Take the conservative end. 34 million miles. The Artemis II distance record represents less than 1% of that figure. Less than 0.8%, to be more precise. The farthest any human has ever traveled from Earth would need to be multiplied by more than 134 just to reach Mars at its closest. And Mars is not far. Mars is our next-door neighbour. Mars is the nearest plausible destination for a crewed mission beyond the Moon. If the farthest distance humans have ever reached barely registers against the trip to our closest neighbouring planet, then the honest answer to how far humans could ever travel begins to look very different from what most people imagine. This is not a story about what we hope to do. This is a story about what physics, biology, and energy will actually allow. Start with the Moon, because the Moon is the only destination beyond low Earth orbit where humans have actually stood. Between 1969 and 1972, 12 astronauts walked on the lunar surface across 6 Apollo missions. Each mission lasted roughly 8 to 12 days. The longest stay on the surface was about 3 days during Apollo 17. Resupply was unnecessary because the crews carried everything they needed for the short trip. Communication delay was minimal, roughly 1.3 seconds each way, barely noticeable in conversation. If something went wrong, Earth was only 3 days away. Apollo 13 proved this. When an oxygen tank exploded on the way to the moon, the crew used the lunar module as a lifeboat and swung around the far side of the moon to slingshot back home. They nearly died, but the option to return existed. The Earth was close, help was reachable, the margin for survival, while terrifyingly thin, was real. This is the crucial characteristic of lunar travel that most people take for granted. The moon sits roughly 240,000 miles away. Light covers that distance in about 1.3 seconds. A spacecraft traveling at Apollo-era speeds can complete the journey in approximately 3 days. If a crew encounters a medical emergency, a hardware failure, or a radiation event from a solar storm, they can abort and return to Earth within a time frame that allows rescue. The moon is hard. The moon is dangerous. But the moon is survivable precisely because it is close enough to maintain a meaningful connection to home. Now watch what happens when you extend that logic to Mars. A crewed mission to Mars, based on current and near-future propulsion technology, would require between 6 and 9 months of transit in each direction. The exact duration depends on the trajectory chosen, the alignment of the planets at launch, and the propulsion system used. Most serious mission architectures use a Hohmann transfer orbit, or a modified version of it, which is the most fuel-efficient path between two planets. This trajectory takes advantage of orbital mechanics to minimize the energy required, but the cost of that efficiency is time. A crew launching on a minimum energy trajectory during a favorable window would spend roughly 7 months coasting through interplanetary space before reaching Mars orbit. 7 months. Not 7 hours, not 7 days. 7 months in a sealed vessel crossing a void where the crew must solve every problem with whatever they brought aboard. Once the crew arrives at Mars, they cannot simply turn around and come home. The planets must realign for the return trip. This orbital mechanics constraint forces crews to remain at Mars for approximately 500 days before the next favorable departure window opens. 500 days on, or orbiting a planet with a surface temperature that averages -80 degrees Fahrenheit, an atmosphere that is 95% carbon dioxide and less than 1% as dense as Earth's, no liquid water on the surface, and no breathable air. The total mission duration, from Earth departure to Earth return, comes to roughly 1,000 days under most proposed architectures, nearly 3 years. 3 years is not a camping trip. 3 years is the time it takes to earn a law degree. 3 years is long enough for a child to be born and begin speaking in sentences. 3 years locked inside a spacecraft and a surface habitat with a small crew, separated from every other human being by tens of millions of miles of vacuum. The isolation is not merely psychological, it is physical, operational, and potentially lethal. Communication delay between Earth and Mars ranges from roughly 4 minutes at closest approach to approximately 22 minutes at maximum distance. A round-trip message can take over 40 minutes. This means that if a medical emergency occurs on a Mars crew, the astronaut cannot call a doctor and receive instructions in real time. By the time the message reaches Earth and a response travels back, the patient could be dead. Every procedure, every repair, every crisis response must be handled by the crew alone, with no external support. Radiation compounds the problem in ways that make Mars qualitatively different from the Moon. In deep space, beyond the protection of Earth's magnetic field, astronauts are exposed to 2 primary sources of ionizing radiation: solar energetic particles, which are bursts of high-energy protons emitted during solar flares and coronal mass ejections, and galactic cosmic rays, which are extremely high-energy particles that originate from sources outside the solar system, including supernova remnants and other violent astrophysical events. Galactic cosmic rays are particularly dangerous because they include heavy ions, sometimes called HZE particles, which can penetrate several inches of solid material and cause severe damage to human DNA. NASA's Mars Science Laboratory measured the radiation dose during its transit from Earth to Mars in 2011 and 2012. The result was 0.66 sieverts for the round trip. NASA's current career exposure limit for astronauts, updated in 2022 to a universal standard regardless of age or sex, is 600 millisieverts, or 0.6 sieverts. A single Mars round trip would already exceed that entire career limit before the crew even set foot on the surface. Add the surface exposure during the 500-day stay, and the total mission dose pushes well beyond any threshold NASA currently considers acceptable for a single astronaut's lifetime. This means a Mars astronaut would likely be restricted to one interplanetary mission in their entire career, and even that single mission carries a measurably increased risk of cancer, cardiovascular disease, and central nervous system damage. Shielding can reduce the dose, but not eliminate it. Galactic cosmic rays are so energetic that even thick layers of aluminum or polyethylene provide only partial protection. Worse, when heavy ions strike shielding material, they can produce secondary radiation, a shower of lighter particles that scatter in all directions inside the spacecraft. In some cases, poorly designed shielding can actually increase the dose to the crew rather than reduce it. Water, polyethylene, and hydrogen-rich materials perform better than metals, but they add significant mass, and every kilogram added to the spacecraft increases the fuel required for launch and transit. Mass is the silent tyrant of spaceflight. Every item a crew needs for a 3-year mission must be launched from Earth's surface, accelerated to interplanetary velocities, decelerated at Mars, and potentially launched again for the return trip. Food for 6 crew members for 1,000 days, water, even with aggressive recycling systems, oxygen, medical supplies, spare parts for every critical system, radiation shielding, exercise equipment to counteract bone and muscle loss in reduced gravity, tools, scientific instruments, habitation structures. The total mass for a crewed Mars mission under most proposed architectures runs into hundreds of metric tons. Launching that mass to Mars requires either an enormous single vehicle or multiple pre-positioned cargo flights sent ahead of the crew. The logistics of pre-positioning are themselves daunting. Cargo missions to Mars must be launched roughly 26 months before the crew departs during the previous favourable planetary alignment. If a cargo mission fails, there is no quick replacement. The next launch window is over 2 years away. A crew that arrives at Mars to find their pre-positioned habitat or return vehicle damaged or missing faces a situation for which no contingency exists. They cannot call for a replacement. They cannot wait for a resupply ship. They are 140 million miles from the nearest help, and the nearest help cannot reach them for years even if it launches immediately. Compare this to the Moon. On a lunar mission, the crew is never more than 3 days from home. Communication delay is negligible. Resupply missions can be launched within weeks if necessary. Solar storm warnings give crews time to shelter. Abort options exist at nearly every phase of the mission. The Moon is a destination where human beings can still operate within a safety margin that allows for mistakes, failures, and emergencies. Mars eliminates that margin entirely. On Mars, every failure is potentially fatal, and every fatal scenario must be solved by the crew alone with the resources they have on hand. There is no abort to Earth option during the surface stay. There is no emergency return vehicle that can launch on short notice. There is no rescue mission that could arrive in less than 2 years. The crew is on its own in the most complete sense that phrase has ever carried. And yet Mars is the easy one. Mars is the nearest planet that humans could plausibly visit. It has a solid surface to land on. It has a thin atmosphere that can be used for aerobraking, reducing the fuel needed to decelerate from interplanetary speeds. It has water ice at the poles and beneath the surface, which could theoretically be extracted and converted into drinking water, breathable oxygen, and even rocket propellant through a process called in situ resource utilization. Its day length is almost identical to Earth's, roughly 24 hours and 37 minutes, which means human circadian rhythms would not be severely disrupted. Its gravity, while only 38% of Earth's, is far more manageable than the microgravity of deep space transit, which inflicts a cascade of physiological damage on the human body that worsens with every month of exposure. Mars is, by every measure, the most forgiving interplanetary destination available. It is the one place beyond the Moon where the engineering challenges, while immense, fall within the plausible reach of technology that either exists today or could be developed within the next few decades. NASA's current planning targets a crewed Mars mission in the 2030s, though the agency acknowledged in early 2026 that the timeline depends on technologies still under development, including advanced life support, radiation mitigation, and a deep space habitation module that does not yet exist. SpaceX, which had previously announced ambitious Mars timelines, disclosed in February 2026 that it was delaying its Mars ambitions by 5 to 7 years to focus on lunar missions. Even the Artemis program's own timeline for returning astronauts to the lunar surface has stretched. In late February of 2026, NASA announced a significant restructuring of the program. The Artemis II mission, originally designed as the first crewed moon landing since 1972, was redesigned into a low Earth orbit demonstration flight. The first actual lunar landing was pushed to Artemis IV. The Gateway Station, a planned orbital outpost around the Moon, intended to support surface missions and serve as a staging point for deeper exploration, was placed on pause. Both Blue Origin and SpaceX, the companies contracted to develop the lunar landers needed to carry astronauts from Orion to the surface, were flagged in NASA oversight reports as lagging behind schedule. The agency's stated goal of landing humans on the Moon by 2028 now appears optimistic at best. If returning to a destination 240,000 miles away, one we first reached nearly 6 decades ago, requires this level of effort and still faces delays, the prospect of sending crews 140 million miles to Mars recedes further into the uncertain future. The National Academies of Sciences released a comprehensive report in late 2025 outlining 4 possible campaign architectures for crewed Mars exploration, each requiring decades of preparatory work. The honest assessment is that a crewed Mars mission remains at least 10 to 15 years away, and possibly longer. The technology is not ready, the funding is not secured, the risks are not fully understood. And Mars, the closest and most hospitable interplanetary target, already pushes human spaceflight to the absolute edge of what is survivable. This is the first critical insight in understanding how far humans could ever travel. The difficulty of crewed space travel does not increase gradually with distance. It escalates in lurching, compounding leaps. The Moon is hard but manageable. Mars is an order of magnitude harder, and the gap between Mars and every destination beyond it is not a gentle slope. It is a cliff. Consider what lies past Mars. The asteroid belt, a broad region of rocky debris between Mars and Jupiter, stretches from roughly 2 to 3.5 astronomical units from the Sun. 1 astronomical unit equals the distance from the Earth to the Sun, about 93 million miles. Jupiter orbits at 5.2 astronomical units. Saturn at 9.5, Uranus at just over 19, Neptune at 30. Each successive destination is not just farther in miles, but exponentially harder in every dimension that matters to human survival. Travel time lengthens from months to years to decades. Communication delay grows from minutes to hours. Solar energy diminishes with the square of the distance, making power generation increasingly difficult. Resupply becomes not just impractical, but physically impossible within any reasonable mission timeline. The outer planets are not simply farther versions of Mars. They represent a fundamentally different category of challenge, one where the constraints that already make Mars almost impossibly hard become so severe that the concept of a crewed mission begins to lose coherent meaning. Voyager 1 offers a haunting illustration. Launched in 1977, it is currently the most distant human-made object in existence. Traveling at roughly 38,000 miles per hour, it has been flying continuously for nearly 49 years. As of early 2026, It sits approximately 172 astronomical units from the Sun, roughly 16 billion miles from Earth. A radio signal from Mission Control takes over 23 hours to reach it. By November of 2026, Voyager 1 will cross the one-light-day threshold, becoming the first human-made object so distant that a message from Earth requires a full 24 hours to arrive. 49 years of continuous flight at 38,000 miles per hour, and Voyager 1 has not yet reached one light day from Earth. The nearest star is 4.24 light-years away. Voyager 1 is among the fastest outbound objects humanity has ever launched, and it has not yet travelled a single light day from Earth. The nearest star is more than 4 light-years away. The gap between what our best machine has achieved in 5 decades and what would be required to reach even the closest neighbouring star is not a gap that incremental progress can close. It is a chasm measured in tens of thousands of years. But that is a problem we will return to shortly. Right now, the question is simpler and more immediate. If Mars already represents the ragged edge of human capability, what happens when we look past it? What happens when the distances double, then triple, then multiply by 10, by 20, by 100? The answer lies in the outer solar system, where every factor that makes Mars difficult becomes catastrophically worse. The gas giants and ice giants are not destinations waiting to be conquered. They are walls, built not from rock or metal, but from time, distance, radiation, and the remorseless arithmetic of energy and mass. What follows next is the story of what those walls look like up close, and why even our most ambitious engineering cannot climb them. Jupiter is the first destination past Mars that anyone with serious ambitions would consider. It is also the destination where the mathematics of human space travel begins to collapse. Jupiter orbits the Sun at an average distance of roughly 484 million miles. Under the most favourable planetary alignments, using a Hohmann transfer orbit similar to what a crewed Mars mission would employ, the transit time to Jupiter stretches to approximately 2 years and 9 months. Not 2 years and 9 months for the full mission. 2 years and 9 months just to get there. The return trip takes equally long, and unlike Mars, there is no solid surface to land on. Jupiter is a gas giant. Its visible features, the swirling bands and the Great Red Spot, are not terrain. They are the upper layers of an atmosphere that grows denser and hotter with depth until it transitions into a sea of liquid metallic hydrogen under pressures millions of times greater than the surface of Earth. There is no ground. There is no place to stand. A human mission to Jupiter would be an orbital mission, a crew circling a planet they could never touch, staring into clouds that would crush any vessel to atoms if it descended too far. But the transit time is not the real problem. The real problem is what happens to human bodies during that transit, and what Jupiter's environment does to anything that enters its domain. Start with radiation. Jupiter possesses the most powerful planetary magnetic field in the solar system. Its magnetic dipole moment is roughly 20,000 times greater than Earth's, generating a magnetosphere so vast it extends millions of miles into space and traps high-energy particles in radiation belts of extraordinary intensity. The innermost radiation belts around Jupiter are so severe that they would deliver a lethal dose to an unshielded human being in a matter of minutes. Even at the orbital distances of Jupiter's outer moons, the radiation environment vastly exceeds anything encountered in interplanetary space. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, was specifically designed to survive this radiation. Its sensitive electronics are housed inside a titanium vault with walls roughly 1/3 of an inch thick, weighing about 400 pounds. Even with this protection, Juno's instruments have accumulated radiation damage over the course of the mission, and the spacecraft was placed on highly elliptical orbits that minimize time spent in the most intense radiation zones. Juno carries no crew, it carries no life support, it carries no food or water or oxygen. It is a machine built to endure what no human body could withstand, and even it takes damage. But the conversation about Jupiter never stays at the planet itself. It always migrates to the moons. When people imagine human missions to the outer solar system, they do not picture astronauts orbiting a ball of gas they can never touch. They picture boots on the ice of Europa. They picture a submarine descending into the subsurface ocean of Enceladus. They picture a suited figure standing on the orange dunes of Titan, gazing up at Saturn's rings hanging on the horizon. These are the images that fuel public enthusiasm for outer solar system exploration, and every one of them obscures a reality that is far more hostile than the pictures suggest. Europa, Jupiter's fourth largest moon, orbits deep within the planet's radiation belts. The surface radiation dose on Europa is approximately 540 rem per day. To put that in human terms, a lethal dose of radiation for a human being is roughly 400 rem delivered over a short period. An astronaut standing on the surface of Europa in a standard spacesuit would receive a lethal dose in less than 24 hours. Even inside a heavily shielded habitat, the cumulative exposure would build rapidly. The ice crust itself provides some protection, which is why proposals for Europa exploration often involve burrowing beneath the surface. But drilling through a layer of ice estimated to be 10 to 30 kilometers thick, in a radiation environment that degrades both electronics and structural materials, with no possibility of resupply or repair from Earth, while maintaining a pressurized habitat and life support system capable of sustaining a crew for years, is not a challenge that any proposed technology comes close to addressing. The ocean beneath Europa's ice is of enormous scientific interest precisely because it may harbor life. Tidal heating from Jupiter's gravitational pull keeps the water liquid, despite surface temperatures of roughly negative 260 degrees Fahrenheit. Hydrothermal vents on the ocean floor could provide the chemical energy necessary for microbial ecosystems. If life exists in Europa's ocean, it would be the most profound discovery in human history, and a robotic probe, not a crewed mission, is the only plausible way to find it. NASA's Europa Clipper mission, launched in 2024, will study the Moon through dozens of close flybys from Jupiter orbit, using instruments that can analyze the composition of material ejected through cracks in the ice. It carries no crew. It requires no life support. It can endure the radiation environment for the duration of its mission because it was designed from the beginning for exactly that purpose. Enceladus, a moon of Saturn, presents a similar paradox of scientific allure and physical inaccessibility. Geysers of water vapor and ice particles erupt from fractures near the South Pole, shooting material hundreds of kilometers into space. The Cassini spacecraft flew through these plumes and detected molecular hydrogen, silica nanoparticles, and complex organic molecules, all consistent with hydrothermal activity on the ocean floor beneath the Moon's icy shell. Enceladus may be the most promising target in the solar system for finding extraterrestrial microbial life, but Saturn orbits nearly twice as far from the Sun as Jupiter. A crewed mission to Enceladus would face every challenge of a Jupiter mission, compounded by the additional years of transit, additional radiation exposure, additional consumable requirements, and additional distance from any possibility of assistance. Titan, Saturn's largest moon, is perhaps the most tantalizing outer solar system destination of all. It is the only moon in the solar system with a dense atmosphere. Its surface pressure is roughly 50% higher than Earth's at sea level. Its atmosphere is primarily nitrogen, the same gas that makes up 78% of Earth's air. Lakes and rivers of liquid methane and ethane flow across its surface, creating landscapes that look eerily Earth-like in radar images. In some respects, Titan is the most hospitable world in the outer solar system for human presence. The dense atmosphere provides natural radiation shielding. The surface pressure means habitats would not need to withstand the extreme pressure differentials required on airless worlds. A human being on Titan could theoretically walk outside in a heated suit with a breathing apparatus rather than a full pressure suit. But Titan's surface temperature averages negative 290 degrees Fahrenheit. Maintaining a habitat at temperatures compatible with human survival in an environment nearly 300 degrees below the freezing point of water requires continuous, enormous energy expenditure. The Sun, at Saturn's distance, provides roughly 1% of the solar energy available at Earth's orbit. Solar panels are effectively useless. Nuclear power is the only viable option, and the reactors, fuel, shielding, and backup systems required would add tens of thousands of kilograms to an already impossibly heavy mission. And the transit time to Titan remains measured in years under any propulsion system that currently exists or is under serious development. The moons of the outer solar system are spectacular scientific targets. They may harbor the answers to the most fundamental questions about life in the universe. They will almost certainly be explored in detail by robotic missions over the coming decades. But the distance, radiation, temperature, and logistical demands of human travel to any of these worlds place them firmly beyond the practical limits of crude exploration. The dream of standing on Europa's ice or diving into Titan's methane seas is vivid, beautiful, and for human passengers almost certainly impossible. A crewed vessel entering Jupiter's magnetosphere would require radiation shielding far beyond anything that has ever been built for human spaceflight. The mass of that shielding would be enormous. Every additional kilogram of shielding means additional fuel to accelerate and decelerate the spacecraft, which means a larger vehicle, which means more structural mass, which means still more fuel. This feedback loop, known in aerospace engineering as the tyranny of the rocket equation, is the fundamental reason why scaling up a space mission is not a linear process. Doubling the payload does not double the fuel requirement. It can multiply it by a factor of 5 or 10 or more, depending on the mission profile. Now add the consumables for a crew of 4 to 6 people, surviving for a minimum of 6 years. That is the approximate total mission duration for a round trip to Jupiter, with a minimal stay in orbit. 6 years of food. 6 years of water, even with 90% efficient recycling systems, because no recycling system is perfectly closed. 6 years of breathable atmosphere management. 6 years of medical supplies. 6 years of spare parts for every life-critical system, because there is no hardware store between Mars and Jupiter, and there is no resupply ship that could reach you within any useful time frame. Consider the medical dimension alone. In 6 years, the probability of a serious medical event among a crew of 6 people is not trivial. Appendicitis, kidney stones, a dental abscess, a bone fracture during extravehicular activity, cancer, potentially accelerated by the elevated radiation exposure. On Earth, each of these conditions is manageable with appropriate medical intervention. On a spacecraft beyond Mars, the crew must handle every medical scenario with the supplies they brought and the skills they trained for. Surgery in microgravity has never been performed on a human being. Blood behaves differently without gravity, forming floating spheres that obscure the surgical field. Anesthesia protocols developed for Earth's gravity may not translate directly to prolonged weightlessness. A crew member who develops a condition requiring treatment beyond the onboard medical capability will simply have to endure it, manage it as best they can, or die from it. The psychological toll of a 6-year mission is another dimension that does not scale proportionally. Isolation studies on Earth, including the Mars 500 experiment conducted in Moscow between 2010 and 2011, confined small crews in simulated spacecraft for up to 520 days. The results revealed significant psychological effects, including depression, sleep disruption, cognitive decline, and interpersonal conflict. And those subjects knew they were on Earth. They knew that in a genuine emergency, someone could open the door. They knew that the experiment would end. A crew genuinely in transit to Jupiter would have none of those psychological safety nets. The door does not open. The experiment does not end early. The nearest human beings outside the spacecraft are hundreds of millions of miles away, receding further with every passing day. Communication makes the isolation worse. At Jupiter's distance, a radio signal takes between roughly 35 and 52 minutes to travel one way, depending on the relative positions of the 2 planets. A round-trip exchange, sending a message and receiving a reply, takes over an hour at minimum and nearly 2 hours at maximum. Real-time conversation is impossible. Video calls are impossible. Even text exchanges carry delays that make them feel less like communication and more like sending letters into a void and waiting for an answer that may not come for hours. The crew is functionally alone in a way that no human being has ever experienced. Now extend the same analysis to Saturn. Saturn orbits the Sun at an average distance of roughly 886 million miles. Using conventional propulsion, a transit from Earth to Saturn takes approximately 6 to 7 years one way. A round-trip mission with a minimal orbital stay would last somewhere between 13 and 15 years. 15 years is not a mission. 15 years is a substantial fraction of an adult human lifespan. An astronaut who departs for Saturn at age 35 returns, if everything goes perfectly, at age 50. Their children would have grown up without them. Their parents might have died. The world they left would have changed in ways they could not predict or participate in. They would return to a society that had continued without them for a decade and a half, shaped by events they only learned about through time-delayed messages. The consumables calculation for a 15-year mission becomes almost absurd. No closed-loop life support system has ever been demonstrated to function reliably for 15 years without resupply or major component replacement. The International Space Station, the most sophisticated long-duration habitat ever built, requires regular resupply missions from Earth, roughly every few months, delivering food, water, spare parts, experiments, and replacement hardware. The station's life support systems experience frequent maintenance issues, including problems with carbon dioxide scrubbers, water recycling units, and oxygen generation systems. These issues are manageable because resupply is always a few weeks away. On a mission to Saturn, resupply does not exist. Every component failure must be addressed with onboard spares, and every onboard spare that is consumed is gone permanently. The radiation exposure for a 15-year mission in deep space would far exceed any current limit for astronaut health. Even with optimistic shielding assumptions, the cumulative dose from galactic cosmic rays alone over 15 years would be several sieverts, well into the range where long-term health effects become not just probable but expected. Cancer risk increases substantially. Cardiovascular damage becomes likely. Central nervous system effects, including potential cognitive impairment, remain an active area of research. But animal studies suggest that chronic exposure to HZE particles, the heavy nuclei found in galactic cosmic rays, can cause measurable declines in learning, memory, and decision-making capacity. Sending a crew on a 15-year mission means accepting that they will return, if they return, with significantly compromised health. Uranus and Neptune push the numbers beyond any pretense of feasibility. Uranus orbits at roughly 1.8 billion miles from the Sun, Neptune at about 2.8 billion miles. Transit times using chemical or even advanced nuclear thermal propulsion stretch beyond a decade each way. A round-trip mission to Neptune would last approximately 30 years. An astronaut who launched at 30 would return at 60, having spent their entire productive adult life inside a spacecraft. The crew that departed would need to be replaced by the crew that arrived, because human beings do not remain physically or psychologically functional for 30 years in the conditions that deep space travel imposes. This is the point where a critical distinction must be drawn, one that separates honest assessment from science fiction. The distinction is between what robots can do and what humans can survive. Robotic spacecraft have visited every planet in the solar system. Voyager 2 flew past Jupiter, Saturn, Uranus, and Neptune between 1979 and 1989, completing its grand tour in 12 years. The Cassini spacecraft orbited Saturn for 13 years, from 2004 to 2017, returning some of the most spectacular images and scientific data ever collected from the outer solar system. The New Horizons probe flew past Pluto in 2015 after a 9.5-year journey, traveling at roughly 36,000 miles per hour. The Juno spacecraft continues operating in Jupiter orbit today. These missions succeeded because robots do not eat, they do not breathe, They do not get cancer. They do not experience depression or interpersonal conflict. They do not need exercise equipment to prevent bone loss. They do not require privacy or entertainment or psychological support. They can be powered by radioisotope thermoelectric generators that produce electricity from the decay of plutonium-238 for decades without refueling. They can be put into low-power hibernation modes during cruise phases and reactivated when they reach their targets. They can tolerate radiation levels that would kill a human in hours. They can endure temperature extremes that range from hundreds of degrees below zero to hundreds of degrees above. They can operate for years without maintenance because they are designed with redundant systems and no moving parts in their most critical components. A robot is the ideal deep space explorer. A human being is the opposite. Every advantage that robots carry, humans lack. Every requirement that humans impose, robots avoid. The mass of a robotic probe is measured in hundreds or thousands of kilograms. The mass of a crewed spacecraft with life support, consumables, shielding, habitation volume, and return capability is measured in hundreds of thousands of kilograms. The fuel required to send a robotic probe to Jupiter is a small fraction of the fuel required to send a crewed vessel, because the crewed vessel is orders of magnitude heavier. The cost difference is proportional. This asymmetry explains why humanity has explored the entire solar system robotically, but has never sent a human being farther than the moon. It is not a matter of courage or ambition. It is a matter of physics. Human bodies impose constraints that no amount of determination can overcome. You cannot will yourself to survive a lethal radiation dose. You cannot motivate your way through 15 years without food resupply. You cannot inspire a closed-loop life support system to function beyond its engineering limits. Voyager 1 crystallizes this reality. Launched in September of 1977, it is currently the most distant human-made object in existence. As of early 2026, it has traveled approximately 172 astronomical units from the Sun, about 16 billion miles. It is moving at roughly 38,000 miles per hour relative to the Sun, a speed it achieved not through continuous propulsion, but through gravitational assists from Jupiter and Saturn in the late 1970s. Since its flyby of Saturn in November of 1980, Voyager 1 has been coasting. No engine burns, no course corrections beyond minor attitude adjustments, just momentum, carrying it outward at the same speed for over 45 years. At that speed, Voyager 1 covers roughly 3.6 astronomical units per year. It crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, in August of 2012, becoming the first human-made object to enter interstellar space. By November of 2026, it will reach the milestone of one light day from Earth, meaning a radio signal will take a full 24 hours to travel from mission control to the spacecraft. Nearly 50 years of continuous flight to reach a distance that light covers in a single day. And Voyager 1 is fast. It is among the fastest objects humanity has ever launched. New Horizons, the Pluto probe, left Earth at a higher initial velocity but carries less speed now. The Parker Solar Probe achieves extraordinary speeds during its close solar passes, but those velocities are directed inward, not outward, and are not sustained in the interstellar direction. For outbound travel, Voyager 1 remains our benchmark. At Voyager's speed, it would take approximately 18,000 years to travel 1 light-year. The nearest star, Proxima Centauri, is 4.24 light-years away. At Voyager speeds, that journey would take over 73,000 years. 73,000 years ago, anatomically modern humans shared the planet with Neanderthals. Agriculture had not been invented. Writing did not exist. Civilization in any recognizable form was tens of thousands of years in the future. That is the timescale required for our fastest outbound probe to reach the nearest star. No human being can survive 73,000 years. No life support system can function for 73,000 years. No political structure, no funding agency, no civilization has ever persisted for 73,000 years. The distance to the nearest star, measured against our best current technology, exceeds the duration of recorded human history by a factor of roughly 7. But even within the solar system, Voyager's journey reveals the staggering emptiness that lies between destinations. After nearly 5 decades of flight, Voyager 1 has not even reached the inner edge of the Oort cloud, the vast shell of icy bodies that marks the outermost gravitational boundary of the Sun's influence. The Oort cloud is believed to extend vastly farther outward, reaching distances measured in tens of thousands of astronomical units. Voyager 1, at 172 astronomical units, has barely entered the foothills. It will not reach the inner edge of the Oort cloud for another 300 years. It will not pass through the outer edge for roughly 30,000 years. The solar system is not a compact neighborhood of planets clustered around a star. The planets occupy a tiny inner region. Beyond Neptune, at 30 astronomical units, lies a vast desert of nearly empty space that stretches outward for tens of thousands of astronomical units. This desert contains almost nothing: scattered comets, frozen debris, and the thinning remnants of the Sun's gravitational influence. A human crew traveling through this region would experience nothing but darkness, cold, and the growing awareness that they are farther from any source of help than any person has ever been. This emptiness is the wall. Not a physical barrier, not a force field, not a line drawn in space, just distance. Raw, stupefying, incomprehensible distance. And distance in space translates directly into time, because speed is limited by the energy available to accelerate, and energy is limited by the mass of fuel you can carry. And the mass of fuel you can carry is limited by the size of the rocket you can build, and the size of the rocket you can build is limited by the materials, budgets, and engineering capabilities of an entire civilization. The tyranny of the rocket equation is not a metaphor. It is a mathematical relationship first described by Konstantin Tsiolkovsky in 1897 that governs all chemical and nuclear propulsion. The equation states that the velocity a rocket can achieve is determined by the exhaust velocity of its propellant and the ratio of the rocket's total mass to its empty mass. To go faster, you need more fuel, but more fuel means more mass, which means you need even more fuel to accelerate that fuel. The relationship is logarithmic, which means each incremental increase in speed requires an exponentially larger increase in fuel mass. For chemical rockets, the practical limit is roughly 10 to 15 kilometers per second of velocity change per stage. To reach Jupiter in a reasonable time frame, you need velocities on the order of 10 to 20 kilometers per second above what is required to escape Earth's gravity. To reach Saturn, you need more. To reach Neptune, more still. Each increment in speed demands exponentially more fuel, and the mass of that fuel must be launched from Earth's surface, which itself requires enormous energy. Nuclear thermal propulsion offers significantly higher exhaust velocities than chemical rockets, which translates into meaningful improvements in transit time and fuel efficiency. Nuclear electric propulsion, which uses a nuclear reactor to power ion drives, can achieve much higher exhaust velocities but produces very low thrust, meaning it accelerates slowly over long periods. Both technologies are under active development. A study presented at the 2025 Lunar and Planetary Science Conference examined fission-powered propulsion for deep space missions and found promising potential for missions to the outer planets, but also identified significant challenges in radiation shielding and system mass. Even with nuclear propulsion, transit times to the outer planets remain measured in years. And years of transit mean years of life support, years of radiation exposure, years of psychological stress, and years of accumulating mechanical failures in systems that cannot be repaired from Earth. This is the reality that separates the solar system into two zones. The inner zone, encompassing the Moon and Mars and perhaps the near-Earth asteroids, is the region where human travel is extraordinarily difficult but conceivably possible, with technology that either exists or could plausibly be developed within this century. The outer zone, from Jupiter outward, is a region where human travel requires mission durations so long, radiation exposures so high, and logistical demands so extreme that the concept of a crewed mission ceases to be an engineering challenge and becomes something closer to a thought experiment. Robots will continue to explore the outer solar system. They will visit the moons of Jupiter and Saturn, searching for signs of life beneath the ice of Europa and Enceladus. They will map the atmospheres of the ice giants. They will extend humanity's knowledge of the solar system in ways that crewed missions cannot, precisely because they are not burdened by the fragile requirements of biological passengers. But human beings will almost certainly not follow them. Not to Jupiter, not to Saturn, not to Uranus or Neptune. Not because we lack the will, but because the physics does not bend to will. The distances are too great. The travel times are too long. The radiation is too severe. The logistics are too demanding. The margin for error is too narrow. And every one of these problems grows worse, not better, as you push farther from the Sun. Beyond Neptune, past the Kuiper Belt, past the scattered disk, past the empty gulf that separates the planets from the Oort cloud, lies a boundary that carries enormous psychological weight for our species. It is the point where the Sun's direct influence ends and the space between the stars begins. 2 of our machines have already crossed it. No human being ever will unless the terms of the problem change in ways that nothing discussed so far can provide. The question that began this story, how far could humans ever actually travel, is about to confront its hardest answer. The heliopause is not what most people imagine. There is no sign, no visible marker, no wall of light or curtain of energy dividing the Sun's territory from the rest of the galaxy. What exists is a gradient, a region where the outward pressure of charged particles streaming from the Sun, the solar wind, weakens until it can no longer push back against the incoming flow of particles from interstellar space. The transition is messy, turbulent, and spread across a zone rather than a line. Voyager 1 detected it over the course of months, observing changes in plasma density, magnetic field orientation, and cosmic ray intensity that collectively indicated it had crossed from the heliosphere into the interstellar medium. NASA confirmed the crossing in 2013, placing the actual boundary passage in August of 2012 at a distance of roughly 121 astronomical units from the Sun. Voyager 2 followed in November of 2018, crossing the heliopause at approximately 119 astronomical units. The 2 crossings occurred at different distances and in different directions, which told scientists something important about the heliosphere's shape. It is not a perfect sphere. It is distorted, compressed on the side facing the direction of the Sun's motion through the galaxy and elongated into a tail on the opposite side. The boundary flexes and shifts in response to the 11-year solar cycle, moving inward when solar activity is low and pushing outward when the Sun is more active. Crossing the heliopause was one of the great achievements of the space age. For the first time, human-made instruments tasted the interstellar medium directly, measuring its density, temperature, and magnetic properties. The data revealed surprises. The interstellar magnetic field was stronger than models had predicted. The boundary region was more complex than expected, with multiple layers and unexpected plasma structures. Voyager's instruments, designed in the 1970s with technology millions of times less powerful than a modern smartphone, were sending back data from a realm that no spacecraft had ever visited. But crossing the heliopause did not mean leaving the solar system. This is a distinction that matters enormously for understanding the limits of human travel. The Sun's gravitational influence extends far beyond the point where its wind dies out. The Oort cloud, that hypothesized shell of trillions of icy bodies, is believed to stretch from roughly 2,000 to as far as 100,000 astronomical units. Objects in the outer Oort cloud orbit the Sun at distances approaching 2 light-years, nearly halfway to the nearest star. Gravitationally, the solar system is enormous, far larger than the heliosphere that sits at its center like a small bubble in a vast ocean. Voyager 1, at 172 astronomical units, has crossed the wind boundary but remains deep within the Sun's gravitational domain. It will not exit the Oort cloud for roughly 30,000 years. It is, in the most meaningful gravitational sense, still inside the solar system, and it's been flying for nearly half a century. This is the context in which the interstellar question must be asked, not as a fantasy, not as a thought experiment, but as a problem in physics and engineering. How far is the nearest star? What would it take to reach it? And could a human being survive the journey? Proxima Centauri sits 4.24 light-years from Earth. In miles, that translates to approximately 25 trillion. Written out, the number spans 13 digits. It is a distance so far beyond human experience that every attempt to visualize it relies on analogies that themselves strain comprehension. If you placed a marble on a table to represent the Sun and another marble 4 miles away to represent Proxima Centauri, the Earth would be a grain of dust sitting 1 inch from the first marble. The entire solar system out to the Oort cloud would fit within a few city blocks. The distance to the next star would require you to leave the room, leave the building, and walk to the other end of town. At Voyager's speed, covering that distance would take over 70 millennia, longer than any civilization has endured. But Voyager was never designed for speed. It was designed for planetary flybys with gravity assists. What about faster options? What about propulsion technologies specifically engineered to cross interstellar distances? Begin with the most mature option. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures and expel it through a nozzle. This produces roughly twice the exhaust velocity of the best chemical rockets. NASA tested nuclear thermal engines under the NERVA program in the 1960s and 70s, successfully firing prototype engines on the ground before the program was cancelled. Modern interest has revived the concept. Several studies, including one presented at the 2025 Lunar and Planetary Science Conference, have examined fission-powered propulsion for deep space missions and found it promising for reducing transit times to the outer planets. But nuclear thermal propulsion does not solve the interstellar problem. Doubling the exhaust velocity roughly halves the transit time for a given mission, which is meaningful for reaching Jupiter or Saturn but irrelevant on interstellar scales. A nuclear thermal rocket traveling to Proxima Centauri would still require tens of thousands of years. The improvement over chemical rockets is substantial in percentage terms and meaningless in absolute terms. You have reduced a 73,000-year journey to perhaps 40,000 years. The crew is still dead long before arrival. Nuclear electric propulsion, which uses a reactor to generate electricity that powers ion drives, can achieve much higher exhaust velocities. Ion drives produce tiny amounts of thrust, but can operate continuously for years, gradually building up enormous speeds. The Dawn spacecraft used ion propulsion to visit the asteroid belt. The concept is proven, but even the most optimistic projections for nuclear electric systems suggest maximum velocities on the order of a few hundred kilometers per second. At 100 kilometers per second, roughly 3 times Voyager's speed, the transit to Proxima Centauri would take approximately 13,000 years, still wholly beyond the lifespan of any human being, any crew, any life support system, any political institution that might fund and manage such a mission. Fusion propulsion represents a more dramatic leap. Nuclear fusion, the process that powers the Sun, releases energy by combining light atomic nuclei into heavier ones. The energy yield per unit mass of fuel is roughly 4 times greater than fission and millions of times greater than chemical combustion. A fusion-powered rocket could theoretically achieve exhaust velocities of several thousand kilometers per second, enabling spacecraft to reach a few % of the speed of light. The problem is that controlled nuclear fusion has never been achieved as a practical power source on Earth, let alone in a compact, lightweight engine suitable for spaceflight. Despite decades of research and billions of dollars in investment, sustained fusion power generation remains a goal, not a technology. The conditions required for fusion, temperatures exceeding 100 million degrees, intense magnetic confinement, and precise plasma management, present engineering challenges that have resisted solution since the 1950s. If fusion power is eventually mastered on Earth, adapting it into a propulsion system small enough and light enough for a spacecraft would represent a second revolution on top of the first. Experts consulted in a 2024 review of interstellar travel challenges estimated that practical fusion propulsion is at least a century away, if it is achievable at all. Even assuming fusion propulsion works, the numbers remain daunting. A spacecraft traveling at 5% of the speed of light, an extraordinarily ambitious figure for any fusion drive, would reach Proxima Centauri in approximately 85 years. That is within the outer bound of a human lifespan, but it means the crew who arrives would be elderly, having spent their entire adult lives in transit. They would have launched as young astronauts and arrived as octogenarians, assuming the life support system sustained them, assuming the radiation shielding held, assuming no critical hardware failure occurred over 8.5 decades of continuous operation in the most hostile environment imaginable. Antimatter propulsion offers the highest theoretical energy density of any known fuel. When matter meets antimatter, the two annihilate each other and convert their combined mass entirely into energy, following Einstein's equation relating energy to mass and the speed of light squared. In principle, antimatter is the perfect fuel. In practice, it is nearly useless. The problems begin with production. Antimatter does not exist naturally in any accessible quantity. It must be manufactured in particle accelerators, one atom at a time, at costs that currently exceed $60 trillion per gram. The total amount of antimatter ever produced by all the particle accelerators on Earth combined is measured in nanograms. To propel even a small spacecraft to a significant fraction of light speed would require kilograms of antimatter. Producing that quantity with current technology would consume more energy than human civilization has generated in its entire history. Even if production costs dropped by orders of magnitude, antimatter presents severe handling challenges. It must be stored without ever touching normal matter, because any contact results in instant annihilation and a burst of high-energy gamma radiation. Storage systems based on magnetic confinement have been demonstrated for tiny quantities of antihydrogen, but scaling these systems to hold kilograms of antimatter for decades aboard a spacecraft is a problem for which no solution exists or is foreseeable. Furthermore, the annihilation process itself produces gamma rays so intense that shielding the crew would require massive amounts of material, largely negating the mass advantage of antimatter fuel. Studies have estimated that only about 40% of the annihilation energy could realistically be captured as thrust, with the rest lost as penetrating radiation that would irradiate the spacecraft and everything inside it. Antimatter propulsion is not a technology in development. It is a concept in physics, separated from practical application by chasms in manufacturing, storage, and engineering that no current research program is close to bridging. This leaves one more propulsion concept that has received serious attention: laser-driven light sails. The idea is elegant. Build a powerful array of ground-based lasers and aim them at an ultralight reflective sail attached to a tiny spacecraft. The photons from the lasers strike the sail and push it forward, gradually accelerating it to a significant fraction of light speed. The spacecraft carries no fuel. All the energy comes from the laser array on Earth. This eliminates the tyranny of the rocket equation entirely, because the propellant, the photons, never has to be carried aboard. Breakthrough Starshot, announced in 2016 by physicist Stephen Hawking and investor Yuri Milner, proposed exactly this. The plan called for a 100 gigawatt laser array to accelerate gram-scale spacecraft, each smaller than a postage stamp, to 20% of the speed of light. At that velocity, the tiny probes would reach Alpha Centauri in roughly 20 years. They would fly past Proxima Centauri and any planets orbiting it, capture images and data, and beam the results back to Earth using the light sail itself as a communications antenna. The return signal would take about 4 years to arrive. The total mission from launch to data reception would span approximately 25 years. The concept generated enormous excitement. $100 million was pledged for initial research and development. Scientists and engineers from leading institutions were recruited to study the key technical challenges. For a brief period, interstellar travel seemed to have moved from the realm of pure fantasy into the realm of ambitious but conceivable engineering. Then the technical realities set in. The challenges were not merely difficult, they were stacked on top of each other in ways that compounded rather than simplified. The laser array would need to produce 100 billion watts of coherent, focused power. For context, the total electricity generation capacity of the United States is roughly 1.2 trillion watts. The laser array would consume nearly 10% of American electrical output during each 10-minute acceleration burn. Building the array itself would require optics several kilometers in diameter, assembled with precision measured in fractions of a wavelength of light. No such system exists. Atmospheric turbulence would scatter and distort the beam unless adaptive optics corrected millions of distortions per second while tracking a target accelerating at thousands of times the force of gravity. Current costs for laser systems of this type run roughly $100 per watt of output. Breakthrough Starshot would need that cost to drop to a few cents per watt, a reduction of roughly 99%, to be economically feasible. The sail material would need to withstand 100 billion watts of focused laser energy without melting, tearing, or deforming, while remaining thin enough and light enough to be accelerated to 20% of light speed in under 10 minutes. Researchers at the California Institute of Technology identified silicon nitride as a promising candidate and made progress on fabrication techniques, including a breakthrough in 2025 that reduced manufacturing costs by a factor of 9,000 using optical lithography. But demonstrating a material in a laboratory and deploying it as a functional 4-meter sail under the full power of a 100-gigawatt laser array in space are separated by decades of engineering work. Communication posed perhaps the most stubborn challenge. A gram-scale probe at Alpha Centauri 4 light-years away would need to transmit data back to Earth using a sail that doubles as an antenna. The signal strength at that distance, even using laser communications, would be extraordinarily faint. Receiving it would require telescope arrays on Earth with collecting areas far larger than any currently planned. The data rate would be measured in bits per second, not megabits. Sending a single image of a planet could take years. By 2025, the project had quietly stalled. A Scientific American investigation reported that only $4.5 million of the pledged $100 million had actually been spent, distributed across roughly 30 research contracts. Key personnel had moved on. The coordinating structure had dissolved. No final announcement was made. The project was placed on indefinite hold, with its future described by observers as murky at best. Breakthrough Starshot demonstrated something important, though not what its founders intended. It showed that even the most optimistic interstellar propulsion concept, one that eliminates the need for onboard fuel entirely, faces engineering challenges so severe that a well-funded, high-profile initiative staffed by world-class scientists could not solve them, or even clearly define a path to solving them within a decade of intensive effort. And Breakthrough Starshot was designed for gram-scale probes, not humans, not life support systems, not habitation modules, not radiation shielding. Chips weighing less than a paperclip, carrying cameras and communications equipment the size of a fingernail. Scaling the concept to carry a human crew is not an incremental step. It is a different category of problem entirely. A crewed interstellar vessel would weigh not grams but thousands or millions of kilograms. The energy required to accelerate that mass to even a small fraction of light speed would exceed the total energy output of human civilization, not for a year, but for centuries. If direct propulsion cannot carry humans to the stars, what about endurance? What about simply accepting a long journey and designing a vessel to sustain its passengers for centuries? The generation ship concept proposes building a self-sustaining habitat, essentially a small world, and launching it on a multi-century journey to a nearby star. The crew that launches would not arrive. Their children would not arrive. Their grandchildren might not arrive. The ship would carry a population large enough to maintain genetic diversity and social stability across dozens of generations, each born, raised, and dying aboard the vessel until the final generation arrives at the destination star. The concept has populated science fiction for decades, but the engineering requirements are sobering. A generation ship would need to maintain a closed ecological system for centuries without resupply. No closed ecological system has ever been demonstrated to function for more than a few years. Biosphere 2, the most ambitious closed ecosystem experiment conducted on Earth, experienced critical oxygen depletion, species die-offs, and agricultural failures within its first 2 years of operation in the early 1990s, maintaining atmospheric composition, water recycling, food production, and waste processing for hundreds of years inside a sealed vessel traveling through interstellar space is a problem orders of magnitude beyond anything humanity has attempted. The social challenges are equally formidable. A generation ship would need to sustain a functioning society across centuries. Governments would need to persist without the external pressures and resources that stabilize societies on Earth. Education systems would need to transmit technical knowledge across dozens of generations without degradation. Conflicts would need to be resolved without the option of separation, emigration, or external intervention. The psychological burden of knowing that you were born inside a vessel, that you will die inside it, that you will never see the sky or feel wind or stand on ground, and that this condition is permanent and inescapable for your entire community, is a burden no human society has ever been asked to bear. Suspended animation, sometimes called cryosleep, is frequently invoked as a solution to long-duration travel. If the crew could be placed in a state of biological suspension for the duration of the journey, the problems of food, water, oxygen, psychological stress, and social stability would be eliminated or dramatically reduced. The crew would sleep through the centuries and awaken at the destination, biologically unchanged. The difficulty is that suspended animation for human beings does not exist and has never been demonstrated. Cryopreservation of individual cells and small tissue samples is possible. Cryopreservation of whole organs is an active area of research but has not yet succeeded for most organ types. Cryopreservation of an entire human body, maintaining cellular integrity across all tissues, preventing ice crystal formation that destroys cell membranes, and then reversing the process to restore full biological function, is so far beyond current capability that it qualifies as speculative rather than theoretical. No pathway from current science to reliable whole-body human cryopreservation has been identified. It may be possible in principle. It may also be impossible. We do not know enough about the problem to determine which. Time dilation offers one final, tantalizing possibility. Einstein's special relativity predicts that time passes more slowly for objects moving at velocities approaching the speed of light. A spacecraft traveling at 90% of the speed of light would experience time at roughly 44% of the rate experienced by observers on Earth. For the crew, a journey that took 10 years by Earth's clocks would feel like only about 4.5 years. At 99% of light speed, the dilation becomes extreme. A journey of 4.24 light years, measured by Earth clocks, would feel like only about 7 months to the crew. This is real physics. Time dilation has been confirmed experimentally with atomic clocks on aircraft and satellites, and with observations of fast-moving subatomic particles. It is not speculative. It is measured fact, and it means that, in principle, a crew traveling fast enough could reach nearby stars within a subjective human lifetime. The problem, as always, is achieving the required speed. Accelerating a crewed spacecraft to 90% of light speed requires energy inputs that dwarf any source humanity has ever harnessed. The kinetic energy of a 1,000-ton spacecraft at 90% of light speed is roughly equivalent to 200 years of humanity's total energy consumption across all sources combined. Producing, storing, and converting that energy into directed thrust is a challenge that no known or proposed technology can address, and the spacecraft must also decelerate at the destination, requiring an equal amount of energy applied in reverse. The total energy budget for a round trip at relativistic speeds, for even a modest crewed vessel, exceeds the energy output of entire stellar systems. Relativistic travel also introduces hazards that do not exist at lower speeds. At 90% of light speed, even a small particle of interstellar debris becomes a devastating projectile. The kinetic energy of a single milligram grain at that velocity is roughly equivalent to the detonation of 28 tons of high explosive. Interstellar space contains roughly 1 atom of hydrogen per cubic centimeter on average, along with scattered dust grains. At relativistic velocities, these particles strike the forward surface of the spacecraft as a continuous bombardment, generating radiation and erosion that would require massive forward shielding. The shielding adds mass, which increases the energy needed for acceleration, which compounds the problem further. Every pathway to the stars leads to the same conclusion. The distances are real. The physics is unforgiving. The energy requirements are civilization scale or beyond. And every solution that addresses one problem, whether duration, speed, or survivability, creates new problems that are equally severe or worse. The nearest star is not merely far, it is far in a way that resists every strategy human ingenuity has conceived. Chemical rockets are too slow by a factor of thousands. Nuclear rockets are too slow by a factor of hundreds. Fusion rockets, if they ever work, might reduce the journey to a human lifetime but impose radiation, reliability, and life support demands that remain unsolved. Laser sails can reach the required speeds but only for payloads measured in grams, not the thousands of tons required to keep a crew alive. Generation ships require closed ecosystems and stable societies sustained for centuries, neither of which humanity has demonstrated. Suspended animation does not exist. Relativistic travel requires energy inputs that exceed the output of the sun. Probes may reach the stars. Small, lightweight, radiation-tolerant, requiring no food or oxygen or psychological support, machines can endure what humans cannot. A gram-scale light-sail probe, if the engineering challenges are eventually solved, could reach Proxima Centauri in 20 to 30 years. A nuclear-powered robotic probe might reach it in a few centuries. Machines are patient. Machines do not age. Machines do not go insane from isolation or die of cancer from cosmic ray exposure. But a human being cannot be made into a machine. A human body requires oxygen every few minutes, water every few days, food every few weeks. It accumulates radiation damage. It loses bone density without gravity. It breaks under psychological stress. It ages, sickens, and dies on timescales measured in decades, not centuries or millennia. These are not engineering limitations that can be solved with better technology. They are biological facts about what a human organism is and what it can endure. Those biological facts deserve closer examination because they are often waved away in popular discussions of long-duration spaceflight as problems that medicine will eventually solve. The evidence from decades of human spaceflight research suggests otherwise. The human body is not merely inconvenienced by extended time in space. It is actively damaged by it in ways that accumulate and in some cases may be irreversible. Bone density loss in microgravity occurs at a rate of approximately 1 to 2% per month, concentrated in weight-bearing bones such as the hip, pelvis, and spine. On the International Space Station, astronauts exercise for 2 hours every day using specialized resistance machines designed to simulate the loading that gravity provides on Earth. Even with this aggressive countermeasure, bone loss continues. Astronauts returning from 6-month stays on the station show measurable reductions in bone mineral density that require 12 to 18 months of recovery on Earth to partially reverse. Some studies suggest that full recovery does not occur, that a portion of the bone loss sustained in microgravity is permanent. A crew on a multi-year or multi-decade interstellar transit would accumulate bone loss far exceeding anything observed on the station even with continuous exercise. The long-term consequences include dramatically increased fracture risk, which on a spacecraft millions of miles from the nearest hospital could transform a minor accident into a mission-ending injury. Muscle atrophy follows a similar trajectory. Without the constant resistance of gravity, skeletal muscles lose mass and strength at rates that exercise can slow, but not fully prevent. Cardiac muscle is also affected. The heart, accustomed to pumping blood against gravity, remodels in microgravity, becoming more spherical and losing some of its efficiency. Studies of astronauts returning from long-duration missions have documented changes in cardiac structure and function that persist for months after return to Earth. On a mission with no return to Earth for years or decades, these cardiovascular changes would progress unchecked. Vision impairment associated with spaceflight is one of the more alarming discoveries of the past 15 years. A condition now called spaceflight-associated neuroocular syndrome affects a significant percentage of astronauts on long-duration missions. The syndrome involves flattening of the eyeball, swelling of the optic nerve, and changes in cerebrospinal fluid pressure, likely caused by the headward fluid shift that occurs when gravity no longer pulls blood and other fluids toward the lower body. Some astronauts have returned from 6-month missions with measurable changes in visual acuity that did not fully resolve after returning to Earth. The mechanism is not completely understood, and no effective countermeasure has been identified. On a multi-decade mission, progressive vision impairment could compromise the crew's ability to perform critical tasks, read instruments, or conduct repairs. The immune system weakens in space in ways that are still being characterized. Studies have documented reactivation of latent viruses, including varicella zoster and Epstein-Barr, in astronauts during and after spaceflight. T-cell function is altered. Wound healing slows. The combination of immune suppression and close confinement with a small group of people in a sealed environment creates conditions favorable for infectious disease transmission, with diminished capacity to fight infection once it occurs. On Earth, an astronaut with a reactivated herpes virus is an inconvenience. On a spacecraft years from medical facilities, an immunocompromised crew facing an infectious outbreak is a potential catastrophe. Perhaps most concerning are the findings published in June of 2024 by researchers at University College London's Department of Renal Medicine, who reported that prolonged exposure to galactic cosmic radiation and microgravity causes structural and functional changes in the kidneys. The study found that conditions inherent to long-duration spaceflight promote kidney damage that could lead to kidney stones and progressive renal impairment. Kidney stones are already a recognized risk in spaceflight due to bone demineralization releasing calcium into the bloodstream. The 2024 findings suggest the problem is more fundamental than previously understood, involving direct tissue-level changes that could compromise renal function over multi-year missions. On Earth, kidney stones are painful but treatable. On a spacecraft in deep space, a crew member with a blocked ureter, sepsis from an infected kidney stone, or progressive renal failure faces a medical emergency with no adequate treatment options. These are not speculative risks. They are documented, measured, peer-reviewed consequences of human spaceflight observed in astronauts who spent 6 months to a year in low Earth orbit, well within the protective influence of Earth's magnetic field, and who returned to full gravity and medical care immediately afterward. Every one of these conditions would be significantly worse on a multi-year or multi-decade mission in deep space, beyond Earth's magnetosphere. With no possibility of return to gravity or medical infrastructure, the cumulative effect of bone loss, muscle atrophy, cardiovascular remodeling, vision impairment, immune suppression, kidney damage, and chronic radiation exposure over a period of decades is not a set of problems waiting for engineering solutions. It is a biological reality that places hard limits on how long the human body can function in the environment that interstellar travel demands. The generation ship concept attempts to sidestep these biological limits by accepting that no single crew will complete the journey, but it introduces its own category of unsolved problems. The closed ecosystem challenge extends far beyond the well-documented failures of Biosphere 2. Every attempt to create a fully sealed, self-sustaining biological life support system has encountered the same fundamental difficulty. Ecological systems are chaotic, and small imbalances compound over time. Soil microbial communities shift, plant yields fluctuate, atmospheric gas ratios drift. Waste processing systems accumulate byproducts that were not anticipated in the design phase. In terrestrial experiments lasting 2 to 3 years, these imbalances required external intervention to correct. On a generation ship, there is no external intervention. A gradual decline in agricultural productivity, an accumulation of trace toxins in the water supply, a shift in atmospheric composition that develops over 50 years instead of 5, any of these could threaten the survival of the entire population, with no corrective option available. The farthest a probe could travel and the farthest a human could survive are separated not by a gap, but by an abyss. Voyager 1 has already entered interstellar space. A future probe might reach another star, but the human body almost certainly cannot follow, not with any technology that exists, any technology under development, or any technology that can be credibly projected from current physics. This means that the answer to the original question, how far could humans ever actually travel, is not determined by propulsion alone. It is determined by the intersection of speed, time, energy, and survival. The outer limit is not a destination. It is a threshold, a point in the progression from near to far where the requirements of keeping a human alive finally exceed the capabilities of any vessel we could build to carry them. What remains is to define where that threshold lies, what it means for our species, and what it tells us about our place in a universe that was never built to accommodate human ambitions. Every journey discussed so far leads to the same intersection. Not a wall, not a single barrier. An intersection where 4 constraints converge simultaneously and where no amount of engineering, funding, or determination can force a path through all 4 at once. Those 4 constraints are speed, time, survival, and energy. Each one alone is manageable at short distances. Together, at sufficient range, they form a boundary as absolute as any law of physics. Speed determines how long a journey takes. Time determines what the human body and the spacecraft must endure. Survival determines the mass and complexity of the systems required to keep the crew alive. Energy determines whether the total mission is physically possible given the resources of an entire civilization. At close range, within the Earth-Moon system, all 4 constraints are satisfied comfortably. Speed is adequate, time is short, survival is manageable, energy is within reach. At Mars range, the constraints tighten dramatically but remain within the plausible limits of technology that could exist within this century. Beyond Mars, the constraints begin to overpower each other. Fix one and you worsen another. Increase speed and you increase the energy required by exponential factors. Extend duration and you multiply the survival requirements beyond what any closed system has demonstrated. Reduce crew size to save mass and you increase psychological risk while reducing the ability to handle emergencies. Add shielding to manage radiation and you increase mass, which demands more energy, which demands more fuel, which demands a larger vehicle, which demands more shielding. The feedback loops are inescapable. They are not bugs in our engineering. They are features of the physics that governs motion, energy, and biological life. And they define, with surprising precision, where the human frontier ends. Consider what a maximally optimistic scenario looks like. Assume technologies that do not yet exist, but that do not violate known physics. Assume nuclear fusion propulsion that works reliably, producing exhaust velocities of several thousand kilometers per second. Assume closed-loop life support systems that function without major failure for decades. Assume radiation shielding effective enough to keep cumulative crew exposure below career limits over a mission lasting 20 to 30 years. Assume artificial gravity through spacecraft rotation, mitigating the bone loss, muscle atrophy, and cardiovascular deconditioning that currently limit long-duration spaceflight. Assume a crew selected and trained to withstand years of isolation with minimal psychological degradation. Assume a civilization willing and able to fund a mission costing trillions of dollars over decades of preparation and execution. Under these assumptions, which are the most generous that honesty permits, what is the farthest a human crew could travel? A fusion-powered spacecraft achieving 5% of the speed of light, roughly 15,000 kilometers per second, could reach a distance of 1 light-year in 20 years. The nearest star at 4.24 light-years would require approximately 85 years of travel. That exceeds a human lifespan under any but the most extraordinary circumstances. Reduce the target distance. A destination at 1 light-year, approximately 63,000 astronomical units, would take 20 years at 5% of light speed. A destination at half a light-year would take 10 years. A destination at a quarter of a light-year, roughly 16,000 astronomical units, would take 5 years each way, producing a round-trip mission of 10 to 12 years including time at the destination. A quarter of a light-year, 16,000 astronomical units, roughly 1.5 trillion miles. That is the approximate range at which a maximally optimistic crewed mission, using technology that does not yet exist but that does not violate physics, could travel and return within a time frame compatible with human biology and life support endurance. It is deeper into interstellar space than any human has ever been by a factor of nearly 100 compared to Voyager 1's current position. It would represent an achievement of engineering so extraordinary that it would stand as the single greatest technical accomplishment in human history, and it would not reach the nearest star. 16,000 astronomical units sounds like an enormous distance, and it is. It would place a crew well into the inner reaches of the Oort cloud, surrounded by scattered comets and frozen debris, orbiting the Sun at the farthest extreme of its gravitational influence. The crew would be farther from Earth than any human being had ever travelled by an almost incomprehensible margin. They would be months or years from any possibility of communication, let alone rescue. They would exist in a darkness more complete than any environment on Earth, surrounded by the faint glow of distant stars and nothing else. But in the context of the galaxy, 16,000 astronomical units is a rounding error. The Milky Way spans roughly 100,000 light-years. 16,000 astronomical units equals approximately 1/4 of 1 light-year. 1/4 of a light-year is 1/4-100-1000th of the galaxy's diameter. If the Milky Way were the size of the continental United States, the farthest a human crew could plausibly travel would be roughly the width of a single room inside a single house in a single city. Not a city block, not a neighborhood, a room. Extend the comparison further. The observable universe contains an estimated 2 trillion galaxies spread across 93 billion light-years. The farthest plausible human journey, 1/4 of a light-year, compared to the diameter of the observable universe, is a ratio so small that expressing it requires scientific notation. It is approximately 2.7 times 10 to the -12th. In plain language, the maximum human range is roughly 3 trillionths of the observable universe. A grain of sand compared to all the beaches on Earth would be a generous overstatement. This is not a failure of human ambition. It is a statement about the universe's scale. The cosmos was not designed for biological travelers. It was not built with rest stops, fuel depots, or distances calibrated to the endurance of carbon-based organisms, with 70-year lifespans and metabolisms that require constant inputs of water, oxygen, and calories. The distances between stars are set by the physics of stellar formation, by the gravitational dynamics of galactic evolution, by processes that operate on scales of millions and billions of years. Those distances are what they are. Human biology is what it is. The mismatch between the two is not a problem to be solved. It is a fact to be understood, but understanding it requires sitting with a discomfort that most popular science avoids. The default narrative of human space exploration is one of inevitability. We went to the moon. We will go to Mars. We will go to the stars. The trajectory is always upward, always outward, always expanding. The narrative assumes that technological progress is unlimited, that every barrier is temporary, that distance is just an engineering problem awaiting a sufficiently clever solution. This narrative is not supported by physics. It is supported by hope, which is valuable but not the same thing. The distinction between what robots can reach and what humans can survive is not a temporary gap waiting to be closed by better technology. It is a structural feature of the relationship between biological life and interstellar distance. Robots can be made smaller, lighter, more radiation tolerant, more patient. They can be designed to coast for centuries without maintenance, arriving at distant destinations long after the civilization that launched them has changed beyond recognition. A robotic probe weighing a few kilograms, powered by a radioisotope generator or propelled by a laser sail, can endure conditions that would kill a human crew in days. The engineering challenges for robotic interstellar probes are severe but finite. The engineering challenges for crewed interstellar travel are, based on everything we currently understand, beyond the reach of any plausible technology. This does not mean no human will ever leave the solar system. It means that doing so would require breakthroughs so fundamental that they cannot be projected from current science. Not incremental improvements. Not better versions of existing technology. Revolutions in physics on the scale of discovering relativity or quantum mechanics. Entirely new understandings of energy, matter, or space-time that are not currently hypothesized, let alone demonstrated. Betting on such breakthroughs is not planning. It is faith. Faith may prove justified, but it cannot be the basis for a serious answer to the question of how far humans could ever travel. The serious answer, grounded in known physics and plausible extrapolations of current technology, is that the human frontier likely ends somewhere in the region between the outer solar system and the near interstellar medium, perhaps a few hundred astronomical units under conservative assumptions, perhaps a few thousand under optimistic ones, perhaps, under the most generous assumptions imaginable, a fraction of a light year. Beyond that, the constraints of speed, time, survival, and energy converge into a boundary that biology cannot cross. This boundary is not fixed with precision. It shifts depending on which technologies are assumed and how optimistically their performance is projected. A civilization that masters fusion propulsion pushes the boundary farther than one relying on nuclear thermal rockets. A civilization that solves closed-loop life support for multi-decade durations extends it further still. But the boundary does not disappear. It moves outward by factors of 2 or 5 or 10, not by factors of 1,000 or 1,000,000. The fundamental constraints are set by the speed of light, the energy density of available fuels, the radiation environment of interstellar space, and the biological requirements of the human body. These are not adjustable parameters. They are the terms of the universe. Within those terms, humanity's reach is extraordinary by any biological standard. No other species on Earth has left the planet's surface. No other species has set foot on another world. No other species has built machines that operate in the vacuum of space, that have flown past every planet in the solar system, that have crossed the heliopause and entered interstellar space. The gap between a creature confined to a single planet and one that has walked on the moon is immense. The gap between walking on the moon and sending astronauts to Mars, if it happens, will be immense again. Each step represents a genuine expansion of what is possible for a biological species on a small rocky world orbiting an average star. But each step also gets harder. The moon required a decade of focused effort by the wealthiest nation on Earth during a period of extraordinary political motivation. Mars will require decades of preparation, trillions of dollars, and technological capabilities that do not yet exist. A crewed mission to Jupiter, if it were ever attempted, would require capabilities so far beyond current engineering that no space agency has seriously proposed one. Each destination demands not just more resources but categorically different solutions to problems that grow exponentially more severe. This exponential scaling is the reason the human frontier has a limit. Linear progress, adding a little more speed, a little more shielding, a little more food, produces diminishing returns against challenges that grow geometrically. To double the range of a crewed mission beyond Mars does not require double the effort. it requires 10 times the effort, or 100 times, and the next doubling requires 100 times more again. Eventually, the resources required to push the boundary one step farther exceed the resources available to the civilization attempting it. This resource ceiling is not theoretical, it is practical and near. A crewed Mars mission would consume a significant fraction of NASA's budget for decades. A crewed Jupiter mission would require resources on the scale of a major national economy. A crewed interstellar mission, even to the nearest star, would require the focused output of an entire planetary civilization sustained over centuries. No human institution has ever maintained a single project for centuries. No economy has ever dedicated a meaningful fraction of its output to a single engineering goal for more than a few decades. The Manhattan Project lasted 6 years. The Apollo program lasted 12. The International Space Station, the longest continuous space project in history, has operated for 25 years and required the sustained cooperation of 15 nations. A crewed interstellar mission would need to sustain that level of commitment for 10 or 50 or 100 times longer, across political upheavals, economic crises, wars, and the ordinary entropy that dissolves human institutions over time. The practical upper limit of human space travel is therefore determined not only by physics and biology but by the nature of human civilization itself. Even if the physics permitted a journey to the nearest star, the social, economic, and political structures required to execute such a mission might exceed what human societies are capable of sustaining. This is not a criticism. It is an observation about the kind of species we are and the kind of projects we can realistically undertake. There is a strange beauty in this limitation. Not the beauty of triumph or conquest, but the beauty of honest reckoning. Every other species that has ever existed on Earth has been confined to a thin layer of biosphere clinging to the surface of one world. Humanity has already broken that confinement, reaching the moon and extending its robotic senses to the edges of the solar system and beyond. The fact that there is a limit, that the limit is far closer than most people imagine, does not diminish what has been achieved. It places it in context. The context is this. Humanity exists on one planet, orbiting one star among 400 billion stars in one galaxy, among 2 trillion galaxies in the observable universe. The observable universe itself may represent a tiny fraction of total cosmic reality. Within this incomprehensible vastness, the volume of space accessible to human travelers is a sphere, perhaps a few light years in diameter at the most extreme theoretical maximum, and more realistically a sphere a few thousand astronomical units across. That sphere contains one star, our Sun, and its system of planets, moons, asteroids, and comets. Everything else, every other star, every other planetary system, every other galaxy, every other structure in the cosmos, lies beyond the reach of human passengers. Probes will go farther. Data will travel farther still. Electromagnetic signals from Earth's high-power radar and television broadcasts have been radiating outward at the speed of light since the 1930s and 40s, forming an expanding sphere of detectable human presence that currently extends roughly 80 to 90 light-years in radius. That sphere contains roughly 10,000 stars. If any civilization within that volume possesses sufficiently sensitive receivers, they may have already detected evidence of our existence. Our data, our signals, our electromagnetic fingerprint can travel distances that our bodies never will. This is perhaps the most honest answer to the original question. The furthest humans could ever travel is measured in astronomical units, or fractions of a light year. The furthest human influence could reach is measured in light years. The furthest human knowledge could extend, through telescopes and instruments that detect light from the edge of the observable universe, is measured in billions of light years. We are a species that can see far further than it can reach, and can reach far further than it can travel. Our eyes outrun our hands, and our hands outrun our feet, and the gap between seeing and touching and walking is the fundamental condition of human existence in a universe built on scales that dwarf biological life. The Artemis II crew travelled 248,000 miles from Earth. They broke a record that had stood for 56 years. It was a genuine achievement, a moment of pride for the species, a reminder that we are capable of extraordinary things when we commit to them. But that record, the farthest any human has ever been from home, represents a distance that light covers in 1.3 seconds, one heartbeat, the time it takes to draw a single breath. In the currency of the cosmos, the farthest humans have ever travelled does not register. Voyager 1, our most distant emissary, has been flying for nearly 50 years and is approaching one light day from Earth, one day of light travel. There are roughly 365 days in a year. The nearest star is 4.24 light-years away. Voyager has covered less than 1/1500th of that distance. The mathematics is not ambiguous. It is not subject to interpretation. It is arithmetic, and the numbers say what they say. The furthest humans could ever travel is not a single number pinned to a map. It is the point where four curves intersect. The curve of speed, limited by available energy and propulsion technology. The curve of time, limited by the biological lifespan of the crew and the mechanical lifespan of the spacecraft. The curve of survival, limited by radiation shielding, life support endurance, and the psychological tolerance of human beings confined in isolation for years or decades. And the curve of energy, limited by the fuel mass that can be launched, the efficiency of the propulsion system, and the total resources that a civilization can dedicate to a single mission. Where those four curves cross, ambition stops and physics speaks. The intersection is not at the edge of the galaxy. It is not at the nearest star. It is somewhere in the dark, cold space between our outermost planets and the barely detectable inner fringe of the Oort cloud, a region that most star charts leave blank because there is nothing there to label. No planets, no moons, no waypoints, just distance, stretching outward into a silence that has existed for billions of years and will continue for billions more. Humanity will send robots past this boundary. We will send signals past it. We will send our curiosity, encoded in mathematics and carried on radio waves, deep into a galaxy we will never physically explore. Our instruments will map stars we cannot visit, detect planets we cannot walk on, analyze atmospheres we cannot breathe. We will know the universe in extraordinary detail, while remaining confined to a tiny corner of it. This confinement is not a prison. It is a condition. The same physics that prevents us from crossing interstellar distances is the physics that allows stars to burn, planets to form, water to flow, and chemistry to produce the staggering complexity of biological life. We are made possible by the same laws that limit our range. The speed of light that isolates us from the stars is the speed that governs the electromagnetic interactions holding our atoms together. The nuclear forces that make interstellar travel so energy expensive are the forces that power the sun and give Earth its warmth. We are creatures of these laws, built by them, sustained by them, and bounded by them. The question was simple. How far could humans ever travel in space? The answer is not a destination. It is a reckoning. The farthest we could go is the point where physics, biology, engineering, and the limits of civilization itself converge into a boundary that desire alone cannot cross. That boundary lies far closer than most people believe, far closer than science fiction suggests, and far closer than our dreams have ever been willing to admit. But it is also farther than any creature born on the surface of a planet has any right to expect. We are stardust that learned to measure the distance to other stars. We are gravity-bound organisms that built machines to escape gravity. We are biological beings with lifespans of decades who have detected light that has been travelling for 13.8 billion years. The gap between what we are and what we have learned to see is the most extraordinary fact about our species. The furthest humans could ever travel is not the end of the story. It is the frame around the story. Inside that frame, everything we have ever done, and everything we will ever do, occupies a space so small that the universe barely notices it. And yet, we notice the universe. We measure it. We describe it. We ask questions about it that have no survival value and serve no evolutionary purpose except to satisfy a need that physics cannot explain and biology did not anticipate. The need to know how far we can go, even when the answer is not far enough. That need is the most human thing about us, and the universe's answer, delivered not in words but in light years and energy budgets and the quiet indifference of interstellar distance, is the most honest thing about the cosmos. We live in a universe that permits us to ask the question and then answers it with a silence so vast that the silence itself becomes the lesson. The farthest humans could ever travel is the place where that silence begins.